Welcome everyone to the lecture on freshwater biomes. So this lecture is going to talk about a different set of aquatic biomes. The last one was marine, and this one is freshwater. So we talked about the salinity of ocean water being roughly 35 parts per thousand. That's what PPT stands for. But there's always going to be some salt in water, so freshwater is not going to be 0 parts per thousand necessarily. Almost every, I would say every body of water, every river, every lake, including freshwater lakes and freshwater rivers, they're going to have some salt dissolved in the water. So we need a cutoff, a threshold for what we consider to be fresh. And that number is less than 0.5 parts per thousand. So if you have less than 0.5 parts per thousand, you are a freshwater habitat. Again, pretty much every single body of water is going to have some salt dissolved in it. What are some examples of freshwater habitats, freshwater biomes? Rivers, streams, lakes, swamps, and marshes, such as this river here, which looks quite similar to what we have in Missouri. That also includes large bodies of water like Lake Superior, which is this one right here. In terms of overall percentage, freshwater makes up less than 1% of the Earth's total water volume. If you remember, 97% of the water is in the ocean, 2% is locked up in polar ice caps, which leaves less than 1% to be found in the freshwater habitats of the planet. And a good chunk of that is found in the Great Lakes, Superior and Huron and Lake Michigan. So the water that we actually see here in Missouri flowing in our streams and rivers and in our reservoirs, super tiny percentage of the total water that we see around the world. Let's start with rivers before we get into lakes. So what is a river? Technically, a river is a collecting channel that drains the world's landscapes, which means, by definition, anything that carries water for a period of time, draining it ultimately toward a larger river, which will ultimately empty somewhere, the ocean, very large lake, whatever it might be. Technically, anything that carries water for some period of time could be considered a river, even the tiny intermittent streams that we have here. I do not have a blue marker, so use your imagination. Here is our river, and the flowing water, some of it's going to seep into the soil, and that's going to seep out from the river, creating wetter conditions than you would have without the river or further away from the river. And what you end up with is this zone along both sides of the river called the riparian zone. It's going to have wetter conditions than, for instance, the land over here, which does not experience that groundwater seepage. In Missouri, we get plenty of rainfall, so you're going to have a lot of greenery out here and a lot of greenery in the riparian zone, but you might have different species that need that additional groundwater seepage or that do better with it. But in the desert, which is what this picture here is showing, and you might want to look at your PowerPoint separately because you probably can't see this too well with my phone recording. But right here along the river, I believe this is the Colorado River out west, you've got greenery right along the river that you don't have even just a couple additional feet away from there. So, band of greenery, more typical desert plant life. And that's because of the seepage of the water from this river channel. So you've got very different species in deserts that can live in that riparian zone. It's much easier to observe this in deserts than it is here. Because like I said, we have enough rainfall that even away from the river, we have plenty of greenery here in Missouri. So be aware of what the riparian zone is and how it causes potentially different plant life to grow there. So we've defined a river. Again, a stream is really just a small river. There isn't a technical term for it. A technical difference between them, I should say. Another term to note is benthic. So if you were to look at a river, and I'm losing my voice, if you were to look at a river, the bottom of the river would be the benthic zone. So just be aware of that term, bottom substrate of a river. So there's this thing called stream ordering, which is used to differentiate between streams that are near the headwaters and streams that ultimately have accumulated many others pouring their contents into them and becoming a much larger river. And if that didn't make any sense, hopefully this explanation will. So, stream ordering starts at 1. A first order stream. These are small creeks. They're going to be shallow, small creeks. The water is going to generally be cool and fast moving. Because of that, there's going to be a large amount of oxygen in that water. Type 1 streams ultimately empty into a second order stream. Second order streams will ultimately empty into a third order and a fourth order, and you can see this visual showing how that works. A fourth or fifth order stream is going to be much deeper and warmer than our first order stream. It's not going to be moving as quickly. As a result of that, you may have lower available oxygen. It's probably not going to have as much clarity, visibility as you would have with the first order stream. Something that might be here would be something like the Merrimack River, for instance, whereas a first order stream would be perhaps an unnamed stream that will ultimately empty into the Merrimack. The Merrimack eventually empties into the Mississippi River, which is a 10th order stream, so you can see it keeps getting higher. But this is a system that's used to describe the characteristics of rivers. And again, it's called stream ordering, that's the official term for it, but river and stream, it's interchangeable for our purposes. Rivers just are generally bigger, right? Ultimately, all streams / rivers are going to either dry out or empty into a large lake or into an ocean or a sea. Here's a map of the U.S. drainage basins, which can give you a good idea of how this works. The Mississippi Basin, which is what we're in, is just massive. And you can see we're right here. So the Merrimack River, it flows and empties into the Mississippi here, which 10th order stream ultimately comes down here into the Louisiana Delta, empties into the Gulf of Mexico. Large rivers such as the Ohio River and the Missouri River empty into the Mississippi as well. In fact, all the way up into Montana, you have rivers that empty into this Mississippi collecting channel. Other drainage basins you can see here. So all of the rivers and streams in this part of California would empty out here to the Pacific. Many of the Great Basin rivers, or actually all of the Great Basin rivers here, would empty into, I'm guessing, the Great Salt Lake. Gulf Coast rivers would empty here into the Gulf, but not into the Mississippi. All of these would empty into the Gulf or the Atlantic Ocean. You can see how these are, how it's organized. And everything up here empties into the Great Lakes. So you've got different drainage basins, ultimately full of streams, rivers emptying into, in our case, the Mississippi, which goes down here into the Gulf. But in the cases of many of these drainage basins, they empty into the oceans or very large lakes. As far as what lives in these rivers or streams, it depends on a lot of factors, and you have very different life in a first order versus a fourth or fifth order stream. A new word here would be biota. I do not believe this word was used in the previous lecture. A river or stream's biota is the life that is present within that river or stream. And that's going to depend on various conditions. So let's compare and contrast a couple of species here to really give you an idea of how this would work. The creature on the bottom is called a hellbender. It's a type of salamander. So let's start with it. In terms of light availability, they tend to hang out under rocks, so I don't think light availability is an important thing for them. But temperature is. They need cold water. And with water movement, they need fast-moving water. Why? Why do they need these things? Well, because colder, fast-moving water has more dissolved oxygen. They need this. They get their oxygen principally through their skin. In fact, their skin is folded so that they have more surface area to get more oxygen. And so if the water isn't moving fast enough or isn't cold enough, they're not going to get enough oxygen to survive. They also have to have thin skin for maximum oxygen absorption, which means very sensitive to pollution. Right? So oxygen availability, they need a lot of it. Right? Nutrient availability, I would put that more as nutrient sensitivity or pollution sensitivity, because a lot of things that people use to grow crops, like nitrogen and phosphorus in their fertilizer, that can make its way into the stream and ultimately lead to algae growth and potentially reduce the amount of oxygen. And so nutrients can harm hellbenders. In contrast to this, you've got the bullhead up here, which is a type of catfish. Bullheads, they thrive in warm, slow-moving, sluggish water with lots of plant growth. They don't need a lot of oxygen. And so places where you find bullheads, you'll pretty much never find hellbenders. And so conserving both requires very different approaches. Bullheads are doing pretty well. Hellbenders are, I believe they are endangered, or they're at least a species of conservation concern in the state. The St. Louis Zoo is doing a lot of breeding of these, because they're not breeding much in the wild anymore. And so they're stocking streams with individuals that were hatched at the St. Louis Zoo. It's pretty cool. lakes. Simply put, lakes do not have the movement that we see in streams and rivers. Now, in Missouri, our definition of a lake is usually a reservoir where we build a dam and then the water level rises, and so you've got something that's shaped kind of like this. Which shows you where the main channel used to be for this stream, with some of the side channels and or places where elevation was lowest, and so that's where the water is going to gather. And so this is usually what we have in Missouri. It's a reservoir, it's not a natural lake, it's man-made. I grew up in Minnesota. Up there, the glaciers carved out and ultimately left over 14,000 natural lakes, which are not shaped like that. And so most of what we're going to talk about has to do with those natural lakes. In Missouri, like I said, most lakes are man-made, including our most famous ones, right? Like Lake of the Ozarks and Table Rock Lake. Those did not exist before we put dams on the river systems. So what is a lake? It is a topographic depression that collects water. Based on that definition, ponds would be counted as lakes because they're a depression that gathers water. Temporary pools that fill up seasonally could be considered lakes. Again, the official terminology for some of these words is very different from how you might use them. We always use lake to be something larger, or to think of it as something larger, not a small pond. But ecologically speaking, lake applies to small ponds as well. In terms of their structure, you can think of them as little oceans, especially when they're bigger. A pond, not so much, but larger lakes, they mirror the ocean in a lot of different ways. This term you might recognize from the previous lecture. The term is littoral zone. And if you think of a lake, which you probably are more familiar with than the ocean, and you think of that region near the shoreline where you have cattails, right? You might have lily pads. That would be considered the littoral zone. That's where you're going to have vegetation growing that is anchored to the ground, but still showing above the water surface. And so you have the littoral zone, which is similar kind of to the neritic zone with the oceans. One thing that you see with lakes in colder areas like Minnesota, for instance, is something called thermal stratification. That just means temperature stratification. So let's take a look at a seasonal journey through a lake's life. Starting with winter. So in winter, you have a layer of ice that forms. By the way, the whole reason that ice floats is because of something called hydrogen bonding. I don't think this was discussed in the previous lecture. Basically, hydrogen bonds cause solid ice to be less dense than liquid water, and so it doesn't actually sink like a solid really should. It floats. And so ice floating means that cold temperatures out here can't freeze the entire lake. This is insulated. And so you've got ice, very, very cold water near 0 degrees Celsius, and then around 4 degrees Celsius for most of the water that's kept beneath the surface. This is super important because you have species like painted turtles and leopard frogs, which live up in Minnesota, and they need to burrow in the mud and the leaf litter under the water. And if the entire lake is ice, because ice would sink and then the whole thing would freeze over, they just can't survive. Fish as well. Fish have to survive under the ice, and so they do that because it floats. Long story short though, you've got ice, you've got cold water, it's pretty uniform. In the spring, the ice melts, It's still pretty uniform. You have what's called turnover. Then we have summer, and we get the stratifying. You've got this upper level of water called the epilimnion. Epi means above or surface. You've got the metalimnion here, and then the hypolimnion where it's cooler. Warm water, cool water. Notice the circulation, there is no mixing. If you go fishing, a number of species will seek out cooler water, and so you'll have to take a different approach in the summer compared to trying to catch them in fall or spring. So epilimnion at the surface, warmer water, hypolimnion, cooler water below, metalimnion separates them. They do not mix until it gets cool in autumn when there is that mixing throughout the lake and you have that fall turnover. So be aware of the levels of stratification that you see in the summer in lakes. And again, this is temperate lakes in the tropics. You don't have these turnovers occurring in spring and fall because you don't have the seasonal temperature variations. But be aware of these. So most lakes throughout the world are freshwater. You've got some like the Great Salt Lake that is not, as you might have guessed by the name, but most lakes are fresh water. In terms of the factors that influence what lives in a lake, water movement, which we saw with rivers, that's not much of a factor with lakes, but oxygen availability still plays a huge part. Now, if you look at freshwater lakes, you can lump them into two different groups, and again, it's not so simple as every lake's going to fit neatly into one of these categories. It's just these are the two tendencies that we see. And the first tendency is for a lake to be what's called eutrophic. There's a pond here, kind that you might see in Missouri. All right, Missouri's natural lakes are ponds. A Missouri pond is a perfect example of a eutrophic lake. All right, eutrophic lakes, they tend to be warm. They tend to be relatively shallow, at least compared to the alternative. Right? They tend to have high amounts of nutrients growth. I should say high amounts of nutrients and algae growth, or algal growth. Plant growth as well. So eutrophic lakes, they have a lot of plant and algae growth. They're relatively warm, they're shallow, all of that meaning they don't have a lot of dissolved oxygen for living things to obtain. So if you're going to live in a eutrophic lake, you have to be adept at getting oxygen when there's not a whole lot there, or not requiring as much. That's assuming you get your oxygen from the water. A lot of species that inhabit these lakes are animals that obtain oxygen through the air, like turtles, frogs, things like that. The other type would be oligotrophic lakes. So oligotrophic are in many ways the opposite of eutrophic, as you might guess. These tend to be cold, deep, with low amounts of nutrients. Not much plant growth or algae, which means lots of oxygen available. Lake Superior, the Great Lakes, at least Lake Superior in particular, is the perfect example of an oligotrophic lake. These things are usually found up north. Think Canada, Minnesota, type north. And you get a lot of salmon and members of the salmon family that live there. But you just don't have the plant growth that you have with eutrophic lakes. and you've got a lot of oxygen up there. There are a lot of things that fall somewhere in between. Some people call those mesotrophic lakes. We're not going to go there, but not everything fits neatly into one of these. There are a lot of things that fall somewhere in the middle. But these are the two opposite extremes, if you will, that we see with lake classification. And last but not least, just a couple of additional freshwater ecosystems. Marshes and swamps, I know you've heard of them. They both occur as transitional ecosystems between land and fresh water. Unfortunately, a lot of them have been drained and modified for agriculture. For instance, if you look at Missouri, I'm going to do a terrible drawing of Missouri here, but if you look at Missouri, right, you've got the boot heel down here. That boot heel region used to be swampland. Most of it was swampland. Now it's almost all farming. 99+% has been drained and converted to farmland. So a lot of it has been changed with marshes and swamps. The difference in terms of marsh versus swamp is that marshes contain vegetation that does not have any woody growth. So a marsh would have cattails, lily pads, things like that. Swamps have trees or other woody shrubs of some sort. So southeastern Missouri used to have cypress swamps because it was dominated by bald cypress trees. And so swamp has woody vegetation like trees. Marshes have non-woody vegetation like cattails and things of that nature. Both of them, again, are transitional ecosystems at the junction of land and water. There are saltwater marshes as well. We talked about salt marshes in the last chapter. Mangroves would be an example of a marine, I wouldn't call it a swamp, but swamp-like in terms of it being dominated by woody vegetation. So that is the freshwater biome lecture.